So, in the previous lecture I solved some problems on motion of charged particle in a magnetic field and electric field, and also we did a problem on calculating the magnetic moment of a loop, current loop, which was not in a plane. So, today I will take up yet another problem where a sphere, charged sphere will be rotated about its diameter, and we will look for the magnetic moment. So, during this solution I would like to introduce many of the ideas, mathematical ideas and connection of this problem with mechanics and all those. So, let us see what is there. So, here is the problem. A uniformly charged solid sphere with total charge q spins with a constant angular velocity omega. So, it spins constant angular velocity omega about one of its diameter. So, this diameter we have picked up and we have called it z axis, this diameter, and about this whole sphere is rotating with this constant angular velocity omega, and you have to find the magnetic moment of this sphere. So, if the charge is uniformly distributed, uniformly charged, and total charge is q, that means if the radius is r, then this is rho, the charge density will be rho, which will be q and then divided by 4 by 3 and pi r cube. R is the radius of this sphere. So, anywhere you take a small volume d-tau, at any place you make a small volume d-tau, and then in that d-tau the charge will be this charge density and then multiplied by that volume. So, that is the meaning of this uniformly charged sphere. So, with this background, let us see how we calculate this magnetic moment. So, what is our basic definition of magnetic moment in such cases? This is a volume charge distribution. It is a volume charge distribution, and it is the current is going in the entire volume, and our definition for magnetic moment will be m is equal to, it was I and then r cross dl, half of this integration for linear current, which we just wrote for the previous problem. If you have linear current, then it is this area vector will be given by this, current times area vector is m. If it is a surface current, then you have a similar expression. This becomes half integration, this I will be there. So, you can write it I by 2 and then r cross dl. So, ideal, for ideal you will write k dA, right. I dl is the current element when you have a linear current, and if the current is on a surface, then you take an area on the surface and then see how much is current is there on that part of the surface, and that is k dA, and so I dl is replaced by this, and if it is a volume current, then this becomes half r cross j d-tau. This is volume current density, this is volume current density j d-tau, this is surface current density k dA, and here it is I dl, we do not call it linear current density, that was a quiz problem. Alright, so this is the definition that we will be using. This is the definition that we will be using. So, m is equal to half r cross j, j is rho times v, okay, this j is rho times v and then this d-tau, and this rho is the charge density which is here, If you go for mass density, it is mass divided by volume, 4, 3 here and pi r cube. So, exactly the same expression, here it is mass, total mass m, and here it is total charge q, and then divide by the volume, you get this mass density and this charge density. So, this rho is here, this rho is here, which is constant, you can take it out. So, this will be equal to half and then integration r cross. This rho you can take out, you can write it here. So, this becomes rho v, velocity. So, you take a point, you take some detour inside, you take some detour inside the volume. In this entire volume you have current, because it is uniformly charged and rotating. So, you take a small detour where? At the position vector r, and then ask what is the velocity of the point there, this small part here, and that is this v. Now, this v is, therefore, you can write this v as omega cross r. Okay. That is the definition of the angular velocity. If an object is rotating with a uniform angular velocity omega, then any point of this object will go with a linear velocity v, and this v will be given by omega cross r. Take some origin on that axis of rotation, from there you measure the position vector r, and then that r cross this omega will give you the direction and the magnitude of the velocity of that point. Different points are moving with different velocities, but then and different magnitudes, and this will give the thing. So, rho I have written, r I have written, v I have written, and now this is detour. This has to be integrated on this entire volume of the solid. So, this you may be knowing this equation, you may be knowing this equation if you have 3 vectors A cross B cross C, then there are 2 terms with a minus sign in between. The first term, this goes out, and these two are dot product of these two, and then this goes out, and in the next term this goes out. So, dot product of these two. So, A dot B and then the vector C, that is this triple product which is here. So, if I use this thing here, what happens? If this will be rho by 2 integration, this will go out. So, r dot r and omega and minus, now this will go out. So, this dot this r dot omega and this r comes here and then detour. Right. Now, take this first term here and let us call it I1. All right, let us call it I1. I1 I am calling integration r dot r and this omega and this detour. First integration of r dot r omega detour, and the second integration will be this. I2 will be the second integration, that is integration of r dot omega, integration of r dot omega, then this r vector and then this detour, r vector and this detour, and then it will be rho by 2 I1 minus I2. This magnetic moment will be rho by 2 into I1 and minus I2. Now, let us work on I1 first. Let us work on this I1 first. This is r dot r, which is r square, omega and detour. Rho also, let us take this rho also, only half will be left. So, let us write rho here, let us write rho here. So, it is rho here, it is rho here. Okay. This omega can be taken out, omega, and let us take this rho inside. So, r square into rho d tau. Correct, what we have done? I1 is rho times r dot r is r square, the distance from the origin, that small volume that you have chosen d tau. What is the position vector of that from the origin, which obviously we will take at the center. So, from here what is this r vector? This is the r vector. Whenever you take that small volume inside this sphere, that is the r vector. So, r vector and dot r vector is this distance square, r square, and omega is constant. We have this omega is constant, we have taken it out, and rho we are writing here. Now, one can do a lot of algebra to calculate this d tau, the volume element d tau, you know, for in spherical polar system it is r square sin theta, then dr, d theta, d phi. You can write all these and then work out and do the integration within proper limits. Not a difficult one. R square into r square will be r to the power 4 integrated with this dr, and then there is no theta phi here. So, just integration of sin theta d theta d phi from 0 to pi, theta going from 0 to pi, phi going from 0 to 2 pi, and that will easily turn out to be 4 pi. So, r integration and then theta phi integration will be 4 pi. But then there is another way you can think of, let us see this r square. This r square is r square rho d tau. Let me write it dm. Let me just write it dm, rho d tau, dm. This rho is 3 times mass divided by this, and this rho is 3 times q divided by this. Only this mass of the sphere is to be is here, and charge on the sphere is here. So, just think in your mind, this is that mass of d tau of this volume. This is the density and this is the volume. So, actually this is charge, but let us write it dm, all right. So, what is this? This is x square plus y square plus z square and then dm, and you check, you can write this as half of 2x square plus 2y square plus 2z square, which I can write x square plus y square then dm, and I write it y square plus z square and then dm, and plus this z square plus x square dm. Check, x square 2 places here and here, y square 2 places here and here, z square 2 places here and here. So, it is 2 times x square plus y square plus z square integrated, and that is this, that is the half into 2 times is this, and this is this. So, we are writing this r square rho d tau, okay, and then I am here. Now, what is this quantity? What is this quantity? This quantity here. So, x square plus y square. This is let us say y, this is x and this is z, and then there is a point somewhere in space, x square plus y square. What is this? X square plus y square is this perpendicular distance. If you drop a perpendicular here, then this is here, and you can reach here by coming to here and then coming to here, okay. So, this is your point x comma y comma z. So, square root of x square plus y square, this is x, this is x and this is y, and the square root of x square plus y square is this length, that is this length, that is perpendicular distance from the z axis, okay. Square of that, square root of x square plus y square is the perpendicular distance of the point x, y, z from the z axis. So it is this square. Now tell me, mass, a small mass here dm, and perpendicular distance from z axis a square, and that has to be integrated on the entire sphere. What is that? That is moment of inertia of the sphere about z axis, and our origin is at the center of the sphere. So, it is a diameter. This is moment of inertia of the sphere about one of its diameter, and how much is that? That is 2 by 5 mr square. 2 by 5 mr square. So, this integration is 2 by 5 qr square. Qr square. This is not mass density. This rho is not mass density. This is charge density. The only difference is in the name. The mathematics just remains the same. This rho is given by, if it is mass, it is given by this, if it is charge, given by this. So, just a change of name, alright. So, this integration remains the same. Instead of finally you write 2 by 5 mr square, you will write 2 by 5 qr square. That is this term. How much is this term? Same. This is moment of inertia about the x axis. This was moment of inertia about the z axis. Z is missing here, x is missing here. This is the moment of inertia about the x axis. That is also a diameter. So, you get the same moment of inertia, and here this is moment of inertia about the y axis, that is also diameter. So, you get the same thing. So, this is same, this is same. So, into 3 and divided by 2, this one. So, this whole integration is 3 by 5 qr square. So, this is equal to 3 by 5 qr square. So, I1 is done. Now, let us do this I2. Let us do this I2, and for I2, where do I do? Let us erase this. So, I2 is rho r dot omega. So, what is r dot omega? This is omega vector, z axis, and this is r vector, and therefore, omega dot r will be magnitude of this omega vector, which is omega, magnitude of this r vector, which is r, and then cos of angle between them, and this is theta. This is theta, standard spherical polar coordinate theta. From the z axis, what is the angle of that radius vector? That is your theta. So, this angle is theta. Hence, this I2 is equal to rho here, which we will take inside, and r dot omega. R dot omega is r, let me write it first, r into omega into cos theta. It is this, and then this r vector. Remember, we have to integrate, and this vector is not a constant vector. This vector is not a constant vector, and therefore, we will have problems. This I1 was rho r dot r omega ditto, actually omega ditto. So, this is okay, this is constant, this direction magnitude is constant. So, no problem in integration, you just integrate. So, only thing you have to do is you have to put this direction. So, that will be in k cap direction. This omega will be omega k cap. So, that k cap also will be carried. So, it is just this this one. But here in the second integration, this is r vector. It does not have a constant direction. So, you cannot add the vectors algebraically, and therefore, you cannot integrate, and so you have to write this as x I cap plus y j cap and plus z k cap, and you have to make 3 integrations, and then this ditto. this omega you can take out, this omega you can take out, this r cos theta is z, omega we have already written. So, now it is x I cap plus y j cap plus z k cap and then rho d tau. Okay. First term, let us first discuss this first term, integration. First discuss this term, z x I cap and then d tau, let us take d tau or rho d tau, does not matter. So, this is dm, rho d tau, rho d tau, let us write dm, z x I cap and then dm. What does this mean? What does it mean? It means that in this sphere you take your dm somewhere here, mass somewhere here, this is x comma y comma z, and then you see what is the z coordinate and what is this x coordinate and multiply. So, you have some x coordinate, y coordinate and then z coordinate is here, and then add all this zx everywhere in this whole volume. So, always we can take a corresponding point here x, y and minus z and make our dm here, right. It will be in the sphere, it will not be outside the sphere. So, for each x, y, z I can have a corresponding point x, y minus z, and x into z here plus x into z here will be 0, right. X coordinate into z coordinate here and x coordinate into z coordinate here at 0. So, since pair wise I can 0 plus 0 plus 0 plus 0 plus 0 plus 0. For any x, y, z I have a corresponding pair point, and therefore, this whole summation on x, z over this sphere will be 0, and so this will be 0. Same will be story with the second term. The second term is z into y. So, it is yz, it is yz and then j cap and then this dm. So, this is z cap constant will come out, you will have yz dm, this is also going to be 0, this is also going to be 0, third term is not going to be 0, it is z into z. It is z into z. So, this I2 is, let me write I2 now, is equal to omega here, integration here, z square here and k cap, and this is dm. That is I2. What is this? What is z square dm? It is not moment of inertia, because about x axis we did it, it is y square plus z square, about y axis it is z square plus x square and so on. But we also know that since everything x, y, z are all symmetric, there is no preference, any diameter you say it is x, any diameter you say y corresponding 90 degrees and then z. So, this z square dm integrated over the entire sphere, that is important, has to be equal to x square integrated over entire dm and also y square dm. The whole sphere is important, otherwise you cannot write such relations. Once it is whole sphere, it is symmetric everywhere, x, y, z are for our, we have put the names x, y, z, all directions are equivalent. So, in z direction you see what is z square dm or x square dm or y square dm, they are all equal. So, you can write this as 1/3 of k cap omega x square dm plus y square dm plus z square dm, and therefore, you can write it this way. So, in place of 1, now I have 3 integrations, but all 3 are equal to each other. Therefore, you add, divide by 3 and you will get this. And once again you can write this as 1/3 and into 1/2 here k cap omega here. Now it is 2x square, 2y square, 2z square. So it is x square plus y square integration dm plus integration y square z square integration dm plus integration z square x square integration dm. Right, it is x square plus y square plus z square. I have put a half here. So now I have 2x square, 2y square, 2z square, and here it is 2x square, 2y square and 2z square. And each of this moment of inertia about a diameter. Each of these is moment of inertia about a diameter, which is 2 by 5 mr square. So we can write this as 1 by 6 k cap omega and then 3 times 2 by 5 mr square. So this is our qr square. It is this. So what happens now? This is 1 by 5. This 2 cancels with this. Oh, 2 into 3 6 here. So it is 1 by 5. So k cap 1 by 5 and then this, yeah, qr square. Omega, where is omega? Where is omega? Oh, this omega we have left, this omega, qr square omega. So qr square omega, qr square omega, 3 into 2 is 6, this 6 cancels out. So 1 by 5 qr square omega, and in k cap direction here it is this 3 by 5 qr square omega. So we have I1, this is our I1, this is 3 by 5 qr square omega. I1 is 3 by 5 qr square omega. This omega is here, and I2 is here. This is I2. This is I2. And therefore, M, the magnetic moment, what was that? What was that? I1 minus I2 and half. Oh, that is erased. It was half here and then I1 and minus I2. Right? When we wrote this, when we defined this I1 and I2, we had that expression on the board which was half times I1 minus I2. We have taken rho inside, and then therefore after that it was only half left. So this is equal to now half I1, here is I1, 3 by 5 qr square omega k cap minus I2 is 1 by 5, and then qr square omega and k cap, and this is equal to 1 by 2 here, 3 by 5 minus 1 by 5 is 2 by 5 here, and qr square omega here and k cap here, and this is 1 by 5 qr square omega in k cap direction. That is the magnetic moment of this rotating sphere. So we will stop here. You could have done it using angular momentum, and angular momentum and magnetic moment, they have relation. Qm is equal to q by 2m times L, and you can write this L as I times omega, and this is just 2 by 5 mr square, and very easily you can get this expression. But my purpose of doing this whole long calculation was, and not to use this, was twofold. One, I wanted to give you a flavor of different beauties of mathematical operations. So that is that you can, if you enjoyed it, it is there, which you will miss if you use this. And secondly, that equation L equal to I omega is not always true. One has to be careful. In this case it is true, but it is not always true. only if something called principal axis. If the rotation is about the principal axis, only then you have this equation. So, one has to be careful before using that. So, we will stop here today.